Welcome to Off Hours, a conversation between John Edwards and Chris Manning.
So a little bit of follow-up from last episode. Listening back to it, I realized I neglected to mention Jessica Edwards being one of the key players involved in that project when we were talking about it last episode as well. So she runs a company called Film First, and she was actually the reason that Greg Jarrell was able to connect with Gary Hustwit, because she had been working with Gary Hustwit, and then by extension, it's also the reason that Massimo Vinelli was able to be a part of Design Canada. So credit where credit is due. Jessica played a big part in this film as well. And someone had also asked me whether I'm related in any way to her, and we are not. I have zero relation to her or the film in any way, other than having enjoyed watching it very much.
John, I noticed that you've added a new tee to your collection of T-shirts that you've designed and made available on Threadless. Looks like you've got a new Escape edition up there.
Yes, felt inspired the other day to whip another one up, a different look, so to speak, than the original Escape tee, which has been the most popular of all the T-shirts that I've ever made. Which is basically just an escape wheel. But this new version is a coaxial take on the Escape tee, and surprising enough, actually, in linking to it, an older tee I had made, which is an ode to free-sprung balance wheels, actually had a big uptick and has outsold this new tee by more than 2.5 times. So I was
That's funny.
Quite surprised by that. Yeah, it is funny. So it's interesting. So that particular tee is now the second most popular, the free sprung blued edition. I noticed as well. There's a certain blog post of yours that is coming up number one in a Google search for multi-lead threading, and I hear was a surprise hit for you as well. So how did that come about?
Yeah, it's funny. You and I have talked about threading a little bit, and we've talked about multi-lead threading a bit, and I think we're going to talk about it a bit more tonight. But I wrote this blog post back in, I'm just looking here, March 19th, 2010. I can't believe it's been more than 8 years since I wrote this blog post. In fact, we were living in our house in Canada at the time. We weren't even living where we are now. I wrote this blog post because partially for myself so that I had the information sitting there, but also because I kept being asked by other pen makers about how to cut multi-lead threads. So I wrote this blog post explaining how they're designed and how to calculate them. And for whatever reason, I hit the zeitgeist of the machining world at the right time, and I've managed to maintain a number one ranking for multi-lead threading on Google. And it is regularly the most visited page on my website, despite the fact that it is 8 years old now. And it really needs a desperate update because I've learned so much since then, and probably needs some better material, including a video. But it's funny how some of these old bits of information get picked up and become popular. And even though, obviously it's not the kind of thing that the average person on the internet is going to be searching for, it just shows us to why it's important to document this information and get it out there, because you never know what's going to be useful and who is actually going to find that information useful. And of course that goes back to my theme for the year of sharing knowledge. So I really do need to get back into updating some of this older material and improving on it.
Yeah, we have touched on threading a little bit in past episodes, but just to make sure everyone is on the same page, jumping back to first principles before we dive into what multi-lead threading is and why you went down that path.
Yeah.
Let's start with just straight up threading. What is threading?
Yeah, threads and screws are something that everybody is used to. In our modern world, they're absolutely everywhere. Everything from the lid on your jam or peanut butter jar to the screws that are holding things together, everything in our modern world relies on some kind of thread somewhere. They're a remarkable mechanical device that is at its core quite simple, but also complicated to make accurately. And it's such an important thing. So when we're talking about screws and threads here, we're talking, if you pick up a machined screw that you would find holding together a piece of equipment, like a piece of electronics or something like that, it's a very fine threaded screw. You do see coarser screws that are used for woodworking, let's say, or maybe holding in a picture up on a wall or something like that, and those are quite coarse screws. But typically, when you and I are talking about screws and threading, we're talking about the finer threads, the more accurate threads that you see, in machined screws. And typically, they're the kinds of things that you would see attached with a nut as well. So you might see a bolt with a nut on it, and that's the kind of thing that we're talking about here when we're talking about our threads.
Mm-hmm. And so, what then makes a multi-lead thread special?
If you're looking at a typical single lead thread, something like a bolt with a nut on it, and you take a Sharpie, let's say, and you put it into the groove at the beginning of the bolt, and you start turning it and don't lift the Sharpie, you'll see by the time you finish turning the bolt so the Sharpie moves all the way down that the entire bolt has now been covered in marker. So that's a single path that goes down the thread, down the entire bolt. In the case of a multi-lead thread, you have more than one track that goes around it. You have more than one lead that goes around the bolt. So you might have something like a 3-start thread or a 4-start thread. In the case of a 3-start thread, if you were to put that Sharpie in one of the grooves, it would travel down the bolt. And by the time you were done passing the Sharpie down the entire length of the bolt, you would have only blackened 1/3 of the grooves that are on that bolt. The other 2 grooves are 2 different threads, and they're related to a different lead that goes down the screw. It's a little bit difficult to visualize even when you're looking at a multi-lead thread, because to an observer who doesn't know what it is, it looks as though it's just a single normal thread, but it isn't. It has more than one thread in there. And probably the most common case of finding a multi-lead thread is actually on the top of something like your peanut butter jar or your jam jar. You might have 2 or 3 leads on that thread, and we'll talk a little bit about why you'd want to do that in a minute. But you can find that if you're turning the cap in the wrong direction, you can feel it skipping over the different leads on the thread. So you might feel that there's 2 or 3 or maybe even 4 of those leads, and you can feel it skipping as you turn the lid backwards on it. And if you try closing it on one of those leads, you'll see that the lid ends up in a different position than if you were to back it off to a different lead and close it. You'll find that it closes in a different position. So that's really what's going on there. You've got more than one thread that runs down that particular bolt or whatever it is that you're threading. That's fundamentally the difference between a single lead and a multi-lead thread.
So what is the particular reason that you desired to have more than one position of rest for the cap of your pens?
Yeah, in my case, it's not so much related to where the cap is going to finish or where it finishes threading on the pen, and it has a lot more to do with how quickly the cap closes. And this is the same reason why a jam jar will be threaded with a multi-lead thread. It's so that you can quickly close it. One of the problems when you deal with a single lead thread, as the diameter increases, the depth of the groove tends to increase dramatically. And if it doesn't, if you continue using a very fine groove for your thread, you have to keep turning it over and over and over again to be able to get it to close. So something like your jam jar, if you were to make that thread using a standard sort of machinist principle, you might have, let's say you wanted to have reasonably fine threads, you might have 40 threads per inch on that thread. Well, if you want to close that lid by a quarter of an inch, that means you would have to turn that lid 10 times to get it to close a quarter of an inch, which is ridiculous. Nobody's going to sit there and keep twisting the lid on the jam jar over and over and over again. And by the same token, if you've got a pen and you want to close the cap on your pen, you don't want to be sitting there twisting the cap 4 or 5 times to be able to get it to close over, let's say, 0.2 of an inch, and so that it can close tightly. People get tired of that. So one of the advantages of a multi-lead thread is that each of those leads is a much coarser pitch than if it was a single lead thread. So when we talk about pitch, that is the amount of distance that the thread moves in one turn. We'll talk about threads per inch if you're talking about imperial threading, and we'll talk about the pitch if we're talking about metric threading. So you might talk about having a 1 millimeter pitch. So in the case of that, if you turn the thread one full revolution, you'll move a millimeter. If you are talking about imperial threads and you're talking about, let's say, 20 threads per inch, then it will take you 20 revolutions to move 1 inch on the bolt, let's say. And so if you do one turn, then you're turning 1/20th of an inch when you do one turn of it. So the advantage of a multi-lead thread is that you can use much coarser pitch, a much coarser thread pitch, while still maintaining a relatively shallow V cut in your thread. And on top of that, you also allow the thread to close quickly. In my case, I'm using a thread that's around a 1/2 inch in diameter. And one of the typical threads that you use on that, like if you were to look up a bolt, let's say a 1/2 inch bolt, you would find that it's typically around 20 threads per inch, which would mean that if you wanted to close the cap on my pen, you would need to turn it around 4.5, 5 times to be able to get the cap to close properly. I've designed a multi-lead thread which has 4 leads instead of 1, and each of those leads is the equivalent of 8 threads per inch. So in the same distance that a typical 1/2 inch 20 thread would close over 4.5 turns, I can get it to close in a single turn. And that means that you get a very nice positive close. It's very quick, and you aren't sitting there constantly twisting the cap onto the pen. It's not something that's necessary in most applications. Again, something like a bolt with a nut that you're using to hold something in place. Typically, a single lead thread is fine for that. But really, the biggest use for multi-lead threads is going to be in this kind of a situation where you want it to close quickly, and you don't want to use a very, very coarse thread. Because in my case, if I used a 1/2 inch thread with 8 threads per inch, and that was all I did it as, it would be a very, very coarse thread. The V cut that I'd have to make would be quite deep, and I would actually cut through the wall of my pen. There's not enough material there to properly cut a 1/2 inch 8 thread on my pen. It would just be too coarse.
So did you do any exploratory work beforehand to figure out the optimal number of leads that you wanted to have on the pen? Like, did you experiment with 3 and 5 and ultimately settle on 4? Or was it just sort of first crack at it, you felt like you liked the feel of it and just ran with it?
I honestly wish I could say that it took me one try to get this right, John. It took me forever. I think I spent about, 3 or 4 months experimenting with different threads before I was happy with something that worked. And for a number of reasons, not just because of the feel, but also to get the thread engagement properly designed and whatnot. So in my case, the things that I knew, I had some restrictions on what I was doing. So I knew that I was working with a thread that was roughly a 1/2 inch in diameter. I knew that I was trying to close the thread in approximately 200 thou, so 2/10 of an inch. And I knew that I wanted to try and keep it down to around a single turn if I could. And I knew that that ended up being somewhere around 8 threads per inch was a good, sort of a good guideline for what I wanted to do. Typically, people don't use odd numbers for threads per inch. Like, you're not typically going to find a 7 or an 8 or a 9. Sorry, you're typically going to find, let's say, a 6 or an 8 or a 10. So I wanted to keep it something that was going to be relatively easy to cut. But I had a rough idea of what the parameters needed to be. And then I started experimenting a little bit. Now, one of the problems that I found when I first started was that I didn't know anything about how to design a thread, because there is some math involved in how to design a thread properly. And I didn't understand that math at all when I first started doing this. I honestly, now I still don't.
Cheat and use libraries.
I do too. And when you look at something, so the book that's in my library that has this information is the Machinist's Handbook. If you ever want to become a machinist, or you're curious about machining, or you're a hobbyist trying to become a machinist, or you're a watchmaker pretending to be a machinist, or a jeweler pretending to be machinist, buy yourself a copy of the Machinist's Handbook. It doesn't need to be the latest edition. They've been printing it since the early 20th century. It's easy to find copies of this book. And it will give you every bit of information and every single calculation you could possibly imagine on how to do everything from design thread to figure out the correct feed rate for cutting a particular material. It's remarkable the amount of information that's inside of this book. The problem is that it doesn't talk about multi-lead threading very much. It doesn't really give you any good details on this. There are standardized threads for nearly all of the single lead threads out there that you could imagine. There's metric threads, there's imperial threads, there's British Association, there's Whitworth, there are more thread styles and types out there that have been used over the last couple hundred years than you even want to try and imagine. And they have information about all that stuff. But if you want to find a multi-lead thread, there isn't really a good standard for that. So I needed to figure out how that worked. And the way that I started with it was just through pure experimentation to see what worked and what didn't. And then from there, I refined those experiments by starting to understand the math better, starting to understand what you're doing better. Threads are a little bit challenging because, unlike turning, let's say, a part that goes inside of another part, that's easy. You turn the outside diameter of one part to closely match the inside diameter of another part. Depending on how tight you want those parts to fit together, you basically turn them closer in tolerance to each other. And you can get everything from a very loose, sloppy fit to a tight interference fit that you have to sort of force, all the way up to a fit which requires you to supercool one part and heat another part before you drop them onto each other. And then as they cool, they then tighten and are inseparable because they're now tightly bound together through friction. With threads, you can't produce an outside thread and an inside thread that are 100% engaged. If you try and do that, they'll bind up and it will never, it will never move. Basically, there's too much friction inside of that thread.
Yeah, in the same way that it's necessary to have play in a gear train between the teeth so that they don't lock up. You need to have play between the teeth or the ridges of the threads.
Absolutely, that's a perfect analogy in terms of watchmaking and clockmaking. If you try and make two gears mesh together absolutely 100% perfectly, they'll bind up, or they'll start chewing each other up, which is bad. And it's the same thing with the thread. If you try making a thread that is too perfect, then it will bind or it will destroy itself as you try closing it. So there was a lot in my case, there was a lot of experimentation early on in how to do this and how to understand it. So one of the reasons why I wrote this blog post was partially to figure out in my own head how this was working, and also to codify it for myself so that when I needed to figure out another thread, I could do it much easier. So this first thread that I use, this is one of my standard threads that I use for caps and barrels, and I've been using it now for the better part of a decade, and it's on the vast majority of the pens that I make. But recently, I started making a pen with a very different threading mechanism for the cap, and I needed to change my threads around. It was no longer a 1/2 inch diameter, and it no longer made sense to use a 4-lead thread that was a 1/2 inch in diameter. So I've created a new thread. This one's actually a 3-lead thread. And this blog post allowed me to go back and sort of figure out, okay, how did I actually do that the first time? So threading is a complicated subject when it comes to the actual math and geometry of threading. And we do know a lot more about it now than obviously we did at one point, but it is complex to figure out properly, especially when you start dealing with something non-standard like a multi-lead thread like this.
Mm-hmm. So what were your reasons for moving to the 3-lead thread?
In this case, because I was moving to a smaller diameter, if I kept a 4-lead thread like I was doing on the larger diameter, the size of the threads themselves, that V groove that you were creating was so small, and it became quite delicate. It wasn't so much a problem in my case, I've always got a metal thread on one side and an acrylic thread on the other side. The threads that I tend to be working with, if I were to make them out of similar materials on both sides, so for instance, if I were to make a silver thread on both sides of it, the silver galls against itself, so it becomes it starts ripping itself apart and it binds up internally, and it means that if I want to have that thread work freely, it has to be very, very loose, and it then becomes sloppy, and it's not a very pleasant experience. So in my case, I will always put an acrylic sleeve, for instance, on the cap, and then have a metal section on the body of the pen, or the metal barrel of the pen is what's threaded. So in this case, with the smaller thread diameter, the section was made out of metal. That was fine. The turning very, very fine threads in metal is easy to do, and it was going to hold up over time. But the acrylic thread that was in the cap was quite delicate, and over repeated use, it was just breaking apart because it was just too delicate. And so I needed a slightly beefier thread. Those V grooves needed to be a little bit deeper and a little bit more robust. And so in this case, I went down to 3 leads, which allowed me to then modify it a little bit and use a slightly deeper V groove for the thread, and it made it a little bit more robust, and it was more durable. And that's one of the reasons why I carry my own pens around with me in the shop. So I have ridiculously expensive pens in my shop because I need to sort of see how they work in the real world in sort of worst case scenarios, and that's basically when I'm using them. So they get closed wrong, they get dropped and things like that, and it's not intentional. I'm not sitting there and dropping a pen repeatedly from the same height all the time, but as I'm using it and as I'm sort of causing these problems, I see how I see how the pens react and what breaks, what doesn't break, and that really, really fine thread was breaking too often. So that's why I ended up changing it, and I'm quite happy with the way that it looks and works.
So is this something that is common at all in other high-end pens or even less expensive pens, given that jam jars use the same technique, or what first brought this onto your radar?
Yeah, I'm certainly by no means the first person to make a multi-lead thread in a pen. Anyone who tells you that they're the first person to do something in a pen is probably they're either lying to you outright, or they just haven't realized that somebody beat them to it, because there has been so much innovation in the pen world, and some of it's ridiculous and outrageous, but there have been so many people who've done so many things in pens over the years. It's not something that people really think about as having sort of an arms race in the pen world, but at one point there was quite the arms race in terms of making innovative additions to pens. So some of that was about how the designs were created. A lot of it had to do with filling mechanisms. If you go back and you look at filling mechanisms from the 40s, 50s, 60s, the filling mechanisms for fountain pens just got ridiculous. If you ever want to see the most over engineered design of any object, look up a snorkel fountain pen and how these snorkel fountain pens were designed. It actually has a little snorkel that, as you twist the back, it extends out from underneath the nib, and that's what you stick into your ink, so you don't get excess ink on your nib as you're filling it. And then you fill the pen, and then you twist it again, and it retracts this snorkel back into the pen. It's absolutely ridiculous.
When I was a kid, the first time I heard about the engineering that went into making a pen for writing in space, one of the first thoughts I had is, why don't they just use pencils?
It turns out they did just use a pencil. They weren't using pencils. They were using, if I remember correctly, I think they were using grease markers. The problem with graphite is that it's electrically conductive. So if the tip of your pencil breaks, you don't want it getting into the electronics in space. Bad things happen.
Fascinating. See, this is why I'm not a rocket engineer.
So graphite pencils are not actually a good thing to use on in spacecraft. So I believe they were using grease pencils. Anyways, yes, the Fisher Space Pen was created and did end up being sold to NASA, but NASA didn't actually commission it. It was something that Fisher ended up creating of their own accord and ended up sort of marketing as the Space Pen, sort of independently. But anyways, that's a different story with different problems. But yeah, I'm certainly not the first person to have created a multi-lead thread on their pen caps. People have been doing it for a very long time. Nowadays, there are two ways that typically people use for closing pens. They either have a snap cap, so there's some kind of a snap mechanism that gives a little bit and it snaps together. And this you tend to find on your less expensive pens. Also, you get a friction fit. So if you have something like the classic Bic pen, you'll see that has just a friction fit on the cap. A lot of inexpensive pens that you'll find in, rollerball pens that you'll find in the stationary cabinet at work, if your work still happens to have a stationary cabinet, a lot of those pens have some kind of a snap together cap. So as you push down on the cap, you'll get this very positive snap as it clicks into place. High end pens these days, they have a tendency to use multi-lead threads to thread together. And so you'll see either something like what I've done where, again, it's a 3-4 lead thread that allows it to close quite quickly. Sometimes what they'll do is a very coarse sort of custom thread that doesn't go very deep, and it's usually has, instead of having a V profile to it, it usually has a very flat profile, so it's almost a square shape to the thread pattern instead of a V shape to the thread pattern. And you'll see that. So, for instance, if you take a look at, let's say, David Oscarson's pens, his tend to use more of a very coarse, flat style to his threads, and so he's not using a multi-lead thread, but he's taking advantage of a coarse thread by creating this custom thread that he's using. So, yeah, I'm not doing anything particularly different or weird than a lot of people are. The new pens that I'm using have a thread at the end of the section close to the nib. And again, that's not anything new. People have been doing that. Like I think the early ones that the earliest ones I've seen were some safety pens from the 20s that were using a thread at the very tip of the section, like what I'm doing. That's where I originally stole my design idea for that. So yeah, this is a fairly common technique in the pen world, and it's something that a lot of people don't want to talk about. Again, people think that this is all, it's secret proprietary information about how they design something. But again, it's all been done before, and it's not, none of this is particularly revolutionary.
So was there a particular high-end pen that you first came across it on, or was it you just got sick of tired of having to screw down the cap a bunch of times and did some research and determined this was your best line of attack?
Well, the earliest pens that I was making were being made from kit pens, and we've talked about those on earlier episodes. You can buy a lot of these kits with some of the hardware already made, including the threads between the caps and the barrels. And those kit pens had multi-lead threads often in them. So you didn't necessarily need to be buying a high-end pen to get a multi-lead thread. So these parts were, I was buying them pre-made and they were like that, but I didn't like the style and the design of the hardware. So that's why I was trying to replace that hardware. Early on though, I couldn't cut my own multi-lead threads, and it was partially because I didn't know how, but also because I was limited in terms of the hardware that I was using. So I was limited to using taps and dies for cutting threads. And this is one of the easiest ways to cut a thread. And a lot of people, if they're a little bit more mechanically inclined, they might have a set of taps and dies in their toolbox in the garage. Usually a pretty basic set. And the tap, it looks like a bolt with the thread that you're trying to cut, and it has, let's say 3 or 4 grooves down the length of it to allow for the chips to clear as you're cutting the thread. So you'll put the tap into a hole, and you'll put a little bit of force on the tap going into the hole, and then you'll start twisting it. And as you twist it, it will actually cut that thread in the hole that you're working in. Conversely, if you use a die, it's typically round and it has a hole through it with the thread cut in there, and then again some grooves in there to relieve it and to create a cutting surface. And if you take that die, put a little bit of force around a rod and start turning it, you'll see that it will start cutting the threads on the outside of that rod. So using these taps and dies, you can then cut the standard bolts or nuts that you would use as necessary for fasteners. And so I was using the standard available taps and dies that I could find on the market. And so at the time I was using a 1/2 inch 20 tap and die for my caps and barrels, which led to the problem of a single lead thread that took a long time to close. So my earliest custom pens were ridiculous to close. Like they would take 3 or 4, sometimes 5 turns to be able to close. And they weren't very satisfying. They were not very well done. So I wanted to replicate what I was getting from the kit pens that I was buying, but improve the look of the kit pens by making my own custom parts. And so that's when I started getting down the road of starting to learn how to cut my own multi-lead threads.
And from your blog post as well, I see you used a classic machinist trick. It looks like you used a Sharpie marker to color the outside of your rod before actually beginning to cut the threads. And you've also marked off sort of your stop point as well. Now, you don't allude to that at all in the article itself, in the writing aspect of it. I think that's a nice little trick worth pointing out as well. Did you find that was particularly helpful?
Yeah, using something like in this case, you're right, it is Sharpie, because at the time that's what I happen to have around. These days, I tend to use Dykem, which is a standard die for the machinists use for marking out and laying out. So it's a layout fluid. You can put it onto a metal part, and it's very durable. It doesn't tend to come off as you work it, other than where you cut away, obviously. And so, yeah, that's extremely helpful when you're cutting a thread for the first time or the first couple times to be able to see what it is that you're doing. Now, it is worth noting that the reason that I was able to cut these multi-lead threads was that I was moving away from a lathe that was just a headstock, basically, without any kind of a lead screw on it. And that lead screw is an important innovation in lathes.
Mm-hmm.
So my earliest lathes, I think I mentioned last time, I started using a tag lathe as my first lathe. So it's a very small lathe. They're great little lathes. They're very precise, but they're limited. They have limitations to them. And one of the limitations on it is that it doesn't have, or at least the ones that they had on the market at the time, didn't have any kind of a lead screw. And a lead screw is attached to the carriage of the lathe. So the carriage is what moves back and forth along the bed and carries the tool. And that's one of the things that allows you to have to turn very precisely with a metal lathe, is that carriage. And the lead screw can be used to drive the carriage back and forth. So it could be used for just turning or moving the carriage at a regular rate so that you get a very nice fine finish on your cut. But it can also be tied into the rotation of the spindle as well. And when you do tie it into the spindle rotation, you can then control the ratio of how fast the carriage moves in relation to how fast the spindle is turning, and therefore the part is turning. And so you can then say, I want this carriage to move 1 inch every 20 times it turns. And that will allow you to cut a 20 threads per inch cut. Or you can say, I want this carriage to move, over a 1 inch distance. I want it to move that 1 inch every 8 times the part turns. And that innovation is sort of one of the foundations of the mechanical revolution and subsequently the industrial revolution. That ability to cut a thread that you know the pitch that you want, that the number of threads of per inch that you want, but you don't have an example of it already, and you want to be able to accurately cut that. And so this principle of being able to cut threads on a lathe using a lead screw, it's incredibly transformational in terms of our ability as creators of machines to be able to make something accurate. And it allowed us to start creating more and more accurate threads, which interestingly allows us to then make more and more accurate machines to make more and more accurate threads. There's a knock-on effect to being able to do that. So this invention of the lead screw and the carriage on a lathe, they're so important to the foundations of our mechanical world and how we can make our current mechanical world.
Yeah, absolutely. You'd hardly give a thread a second thought today as just an average person going about life, but it really was a transformational technology, and the ability to make threads precisely was also incredibly transformative. I finished reading The Perfectionists by Simon Winchester a couple weeks back, and in that book he references a gentleman named Henry Maudsley, who pioneered a very early version of the slide rest, and he was basically snapped up by Joseph Bramah, who was a lockmaker at the time. And we're talking like 250 years ago.
Yeah, it was like late 18th century, I think.
Yes. And this fellow, Henry, was brought on board by Joseph before he had even finished all the regular apprenticeship and journeyman type stuff. And he brought him in-house because the thing that Henry was good at was devising tools to make the parts, to get that repeatability, which was incredibly important for making locks. And he could do it very precisely, which again, incredibly important for making locks. But this being a lockmaker, what was fascinating that stuck out to me, and why this is coming to mind for me now, is that Henry actually turned an incredibly long thread that was perfectly made, and you could spin a bolt from one end to the other, and there's something like 5 feet long. And the firm actually put this out on display on a velvet cushion in the street window, because this was such a remarkable breakthrough at the time, because to get that regularity of pitch between each and every one of the threads was unheard of at the time. If you tried to cut anything that long that was threaded, and then you went to try and spin a bolt onto it, that that bolt would just snag and
Yeah, it would bind.
not be able
Yeah.
to exactly because the regularity and perfection of those threads just wasn't there. So it really is a pivotal technology that paved the way for a lot of other technologies to be made, like things like your slide rests and your lead screws. Like they made it possible to make ever more precise things. It's yeah, we take it for granted, but it's a fantastic technology.
I think it's worth noting that screws and threads and that kind of this kind of technology, this has been known by humans for a very long time. The classic example of it is an Archimedes screw used for moving liquid from a lower area up to a higher area easily. That Archimedes screw is based upon a thread design. Again, if you take a look at the printing presses that Gutenberg, for instance, was using,
Mm-hmm.
or any number of things, a wine press, right? All of these technologies are all taking advantage of a thread of a screw. But it's important to realize that those threads were, first off, they were not very accurate in comparison to what we create today. They were not very accurate. They were very coarse. And the reason that they were so coarse and inaccurate is because they were being carved by hand, typically out of wood. And it was a time consuming effort to cut one of these screws, and they were very inaccurate. Certainly not accurate enough that you could easily put them through a nut, for instance. And obviously, when you start dealing with the screws used in printing presses, those were screws being put through nuts. But again, they were nowhere near the level of accuracy that we see today on screws, or even 250 years ago. The ability to accurately cut a screw was certainly a huge leap forward, and was quite remarkable.
So, what lathe did you end up settling on after the tag?
Yeah, after my tag, I had I guess the two lathes that I bought afterwards. One of the things you're going to find as we talk about machines over many episodes is that I have a bit of a lathe problem. The correct number of lathes I've determined to own is n plus one, n being the current number of lathes you have, and so I keep buying more lathes. And early on, I had the tag lathe, and then I ended up buying a Logan lathe, which was actually from the early 1940s. It was an American lathe, and this particular one had lived on a battleship during World War II. It was actually being used as a machine for being able to repair the ship, and it eventually made its way through a high school and then to me. And it was a nice little lathe. That it had its problems, but it was a good little lathe. And then eventually, I ended up buying a 10 by 22 lathe from Taiwan, much more modern lathe that was much easier to use in many ways than the Logan. But those two lathes were what allowed me to then start cutting multi-lead threads properly, because I could tie the rotation of the spindle into the motion of that carriage, and then accurately cut screws using those principles.
So, what were some of the techniques or measures that you took to be able to cut these perfectly imperfect screws so that they wouldn't bind when you're creating these multi-lead threads?
Part of this is that you do have to create a thread that is not completely perfect, not the sort of the ideal thread. There is one thing that does have to be accurate, and that is the pitch of the thread. How many times that that carriage is moving across an inch.
Mm-hmm.
That is critical that you do it, because if you don't have a consistent pitch, or if the pitch isn't the same between your bolt and your nut, then it's going to bind, and it's never going to work properly. So the first part of it is tying in that movement together, and that's done through gears. There's a set of change gears on the back of the headstock of the lathe that you put together in a correct combination and ratio to then move the carriage in the the speed that you want it for the particular pitch. So that was the first thing, was getting that thread pitch accurate and making sure that you had the correct gears. And in some lathes, like the Logan lathe, it's more challenging because every time you want to change the number of threads per inch that you're cutting, you have to go in, look up the chart with all of the correct change gears, mess about with these gears that are covered in grease, and change to the correct ratio of gears. And there was usually anywhere from 3 to 6 gears that you were changing regularly in the back of this lathe to be able to change from one thread pitch to another. So that was awkward, and it would take 5 or 10 minutes to dig out the book, find the right gears, take them off, clean them up, put the new gears on, lubricate them properly, make sure that it was actually moving the right way. So that was always a pain. With the more modern lathes, there's a quick change gearbox on the lathe itself. And so it's usually just a question of modifying some dials and some levers to get the correct combination of threads that you want, or the correct combination of gears, I should say, that you need for the thread that you want to cut. Once you do that, it's then a question of making sure that you've got an accurate cutter. And in the case of modern V threads, the threads that most people are used to seeing on a bolt, that's using a 60-degree cutter, and it cuts a very nice V thread in the part. And that 60 degrees is chosen because it's a balance between making something that's easy to machine, something that will remain tight to itself so that it will actually close and be reasonably tight, without generating so much friction that it can't be turned on itself. So a 60-degree cutter, a well-ground 60-degree cutter, nice and sharp, that was important. And then you're typically cutting these anywhere from 80 to 60% engagement. So if you were to be able to screw the bolt into the nut and then cross-section that part, the two parts together, you would see that there would only be between 60 and 80% of those two V's actually gripping each other inside of the thread. And that would change depending on the materials that I was using, how accurately I wanted it to fit and feel, that kind of thing. So it changed up a lot depending on what it was that I was doing. And some of that's a question of just experience. Some of that's a question of experimentation, and then saying, okay, that's what I like. And so you start to develop recipes for, okay, this particular pen, I want to cut these threads using these dimensions. That pen I want to actually do a little bit differently because it's using different materials. So some of it's just experience and experimentation.
And for doing the sort of the opposite thread from what you have on display and
right, the female thread,
the blog post there, cutting into the acrylic. Yeah. Did you have to make a custom tool to be able to get inside of that deep enough?
No. Fortunately, I don't. Those kinds of internal threading tools are actually quite common, and because this is being able to cut threads on a lathe. It's one of those things that if you talk to a machinist, especially somebody who's working in a job shop, machine shop, you'll find that they cut threads all the time. Often they're cutting them with a tap and die, so it's not that bad, but you'll see that they're often cutting threads using a V thread cutter. And this is what's typically referred to as single point threading. You have a single point on the lathe tool, and that's what's cutting the thread, versus a tap or die where you have multiple points cutting the thread simultaneously. So single point threading is extremely accurate because you're usually cutting the part on the lathe after you've turned it. So it's perfectly concentric to the part that you've just turned. And so it's very, very accurate. You have a great deal of control over the depth that you're cutting into it. So you can sit there and you can cut a little bit of the thread because you're going to be cutting this in multiple passes. You're going to cut it. You can then try the nut that you're threading the bolt for. Okay, that's not quite right. cut it a little bit deeper, and then you can again check the engagement and make sure, okay, does this feel right? So, when I'm cutting the threads for my pens, I'll usually start with one side of it. So I'll have, let's say, the barrel cut, and then I start threading the cap. And as I'm threading the cap, I'll go in and I'll check the barrel and make sure that it's not too loose, not make sure that it's not too tight still. And so I can sort of tune each thread so that it's just right for what, for that particular pen.
Nice. Now, I'm presuming that the cap has the 3 or the 4
Yeah.
leads as well to match. It's not just a single lead that'll randomly pick one of the others. And do you find that it's consistent no matter the orientation that it's dropping in on, or is there ever any sort of like a rougher course than another if you happen to start on the wrong lead?
That really comes down to the operator and how much he's paying attention while he's cutting the threads. I've my early threads were very inconsistent, and you would find that if you try one lead over versus another, you would find that some of them would work better than others. As I've gotten better at cutting threads, my threads are more consistent now, and they don't have that problem. For production stuff now, I don't thread everything by hand anymore. It's just too time consuming, and it's too easy to make a mistake. If you're not paying attention, you can cut a little bit too deep, and now all of a sudden your thread is too loose. So these days I cut all my threads using a CNC lathe just because I want that consistency.
Mm-hmm.
So that when you thread the pen, when you thread the barrel onto the cap, it doesn't matter which lead you pick. You're going to get the same feel. It's going to close the same way. You're not going to get any binding or anything like that. So yeah, these days I don't have any problems with that on my lathe, on my parts at all, just because I am cutting them on a CNC lathe. And that's really the biggest advantage of that CNC lathe. And that's primarily what I use it for these days, is threading. And it's really just to save me time and increase accuracy, because people are spending a lot of money on a pen, even if they're not spending a lot of money on a pen, even if they're they're spending less than $100, which I guess for a lot of people that is still a lot of money on a pen. They want something that works consistently. They want it to feel nice. And I could spend 45 minutes cutting the cap and barrel thread on a pen, and it would be 95% right most of the time. Or I can cut it on my CNC lathe, and it can take, it takes 5.5 minutes, and it's perfect every single time.
Mm-hmm.
And so it just doesn't make sense for me to spend the time to cut them manually and do it like that, because it's just too easy for me to make a mistake.
From the pictures in your post as well, looks like these were all chamfered starts on each of the threads. Did you find there were any special accommodations you had to make there to get them to work right, or did it just kind of work out of the box?
No, the chamfer makes a big difference when you're cutting them, and again, nowadays I've gotten a standardized sort of chamfer on each thread. I know how much I want to turn that chamfer down to the beginning, what angle I want it at, and that kind of thing. And it certainly does make a difference. It helps with those threads starting to engage when you initially put the pen together, in my case. So that is important, having some kind of a chamfer there to start out. And you'll see that the chamfer itself should decrease down to just before the very tip, the very deepest V of the thread, the very root of that thread. Your chamfer should just make that disappear. And that way, when you put it in, first off, it has a way of engaging, and it seats nicely into the nut. And then as you start to turn it, it'll then grab the thread quickly and start to engage it quickly, and then it'll start to work properly. If you try leaving that leading edge square so that there's no chamfer there at all, you'll find that thread at the very leading edge is very weak. It will break apart, and it'll start to disintegrate quickly, and it doesn't feel good. It gets kind of gritty, and it's not a very nice not a very nice feeling. So
Hmm.
a well-made thread should have some kind of a chamfer there to sort of ease into it and make it a bit easier to close.
Yeah, chamfered starts are probably the most common form of the beginning of a thread out there. An interesting
Yeah.
thread start that I came across my radar recently is called the Higby start. Have you heard of Higby thread
No, I
before?
haven't.
Yeah. It's common on like fire hydrants and fire hoses and things like that, and it has a very abrupt beginning to the thread, and some of the reasons or the merits of this blunt start to the thread is that it prevents cross threading, and then also in the case of fire hoses and hydrants and things like this, because it is such a big coarse thread as well, this blunt start can actually bust through ice or any sort of buildup as
Hmm.
well. But the cross threading was definitely a big perk to it, because you definitely don't want to end up with a cross thread when you've got the kind of pressure coming out of a fire hydrant that you do.
Absolutely. Okay, I see what they're doing with the Higby thread. Yeah, that would definitely help with cross threading, and that's the kind of thing that you could use to some degree on a pen. Although in the case of a pen, hopefully you're not going to be trying to break through ice on the thread of your pen. If you've left your pen outside and it's iced up, you might want to let it melt before you try threading the cap on. The other one that's common that's used for quickly closing threads is a breech thread, and that you'll actually have grooves that run lengthwise to the cylinder. It allows the two parts to slide into each other, and then you just twist it slightly to lock the threads together. And it's called a breech thread because it is used in the breech of large guns, and
Oh,
it
interesting.
allows them to be quickly closed, and then a short twist, then you get complete engagement of the thread. And that's important because in that case you need the structural strength of a long thread, just because of the forces that are coming from the gun itself as it's firing. But you don't want to have even a multi-lead thread would take too long to close when you're in a situation where rapid fire is important.
Hmm.
And when I talk about guns here, I'm talking about artillery pieces. I'm not talking about something that you would hold in your hand. So that breech is designed to be able to close in one sweep and then twist maybe a quarter turn, and you then have a long engagement of thread. And it's an interesting design. I've thought about doing it on a pen cap. It's unfortunately a pen cap's a little bit small to do that on. It's a little bit of a delicate thread to try doing a breech load like that or a breech thread like that. But it's that's an interesting design change to threading as well. Now, something I should actually mention, going back a little bit to when we talked about the idea of the carriage on a lathe and having it driven by a lead screw, and being able to accurately cut a thread on a lathe using that lead screw. That wasn't the first way of being able to cut a thread on a lathe. If you go back earlier than that, in fact, this is starting in the sort of the early 16th century, when you actually get into the ornamental turning engines that were out there. They had ways of cutting threads, but they were using a follower. And the interesting thing with that was that you had a follower that was attached to your tool, and it would follow an existing thread to cut the new thread. And the problem with that was that you had to have a follower and a master thread for every single thread that you wanted. If you wanted an 8 thread per inch count, you needed to have a follower and a master thread that was 8 threads per inch. If you wanted to have then a 10 thread per inch thread, you had to make a new follower and a new master thread. And so it was a good system, and it was certainly useful before we had that lead screw technology. But unfortunately, it required that you already have a thread to work with. So of course that means that the first thread that you're using has to be one that somebody else has cut for you, or that you've cut by hand. And so that leads to problems of inconsistency and, inaccuracies in those threads. And it means that if the supplier of your lathe had a low quality thread as the master, if there was a problem in there, then every single thread that you cut on that lathe is going to replicate that problem. When you start getting into the lead screw, you still have a problem with that lead screw potentially driving error in your part, but because of the way that the gearing ratio works, those errors end up being minimized in use. So it means that you end up with a more accurate thread than necessarily your lead screw could be, just because it ends up sort of fixing some of those problems. So certainly the lead screw is not the first means of accurately cutting threads on a lathe, but it was certainly the best, because it meant that you could do it without the need of having an exemplar previously designed for you.
Well, thank you for all this information, Chris. It's been an enlightening episode. Are there any other caveats that you think are worth noting before someone endeavors to make their own multi-lead threads, or any changes you'd make to your posts now, looking back at it with 8 years of hindsight?
Yeah, I'm certainly going to revisit this post and give some better information. There's certainly some changes and some additions to this. I think the biggest thing that I would add to this post is a video. I think that this is a subject that, while we've been discussing it, I think it's going to be difficult for some people to follow, because they're not used to this. They're not used to seeing a thread and visualizing how a thread works. So I think that it's this is one of those subjects where having a visual aid in front of you is certainly going to be useful, and that's something that I need to add to this particular post is a video add-on to it, so that it can be improved. I think also a little bit of the math is I would expand a little bit on it and make it a little bit more generic than what it is. I'd also probably expand the bit about CNC work, because, as I said, these days I tend to do this through a CNC lathe versus doing it manually. And I think it's important to know how to do it manually. If you are going to sit down and start learning how to thread on a lathe, taps and dies are a great way to thread. If you can get a tap and die for the thread that you want to use, then I would highly recommend that you do it. That's the first thing. You can get multi-lead taps and dies, but they're all custom made, and they're unbelievably expensive. Oftentimes a set will cost you $200 American for a set of taps and dies for one particular thread. And of course, that means that if you decide to change something in your design, you then need to get another set of taps and dies to use the new, for the new design. So it's worthwhile, if you're going to do multi-lead threading, it's worthwhile learning how to do it on a lathe without using a tap and die, because using taps and dies it's too expensive to do. So that's the first thing. It's certainly worthwhile learning how to do it manually. The other thing that I would probably do is I would probably send people away from the idea of doing this using imperial threads and use metric threads instead. It's so much simpler to do the math and to conceptualize what's going on when you're dealing with thread pitch instead of threads per inch. Because anytime you're dealing with threads per inch, you're going to have to convert it to thread pitch anyways, to be able to adjust where the start point of the next cut is for the next lead. And it's just so much easier to do. Frankly, everybody should be using metric anyways for this stuff. If you're still out there using imperial, get out of the dark ages. Imperial stuff, I know obviously in a lot of machining, we're using decimal imperial, so we're not actually using fractions and things like that. But still, we're relying on older standards like threads per inch, when thread pitch is really far superior for this kind of thing, and certainly working in metric for this kind of thing is much easier to do, and it's that's probably the biggest thing I would recommend is try to avoid doing these things and designing these threads in imperial, and instead do them in metric.
And another fascinating tidbit from The Perfectionists, just the book I mentioned a little earlier in the episode, is the final bit of the book, sort of the author's closing thoughts. He dives a little bit into the metric system and the SI units, or the International System of Units. SI stands for the Système International d'Unité. It was surprising to learn just how many units have been boiled down to being defined by time now. More than half of them are defined by time, which I found to be intriguing.
It's funny because the original SI units were all based on the meter.
Mm-hmm.
They were all based on that length. So when you take a look at, you have your original meter, and then you want to create a unit for volume. Well, a liter is a tenth of a meter by a tenth of a meter by a tenth of a meter. And when you look at a kilogram is a liter of water. It's all based around that meter originally, which is interesting. But now that meter has been defined by, I believe it's defined by the length of a particular wavelength of light, or the number of repetitions of a wavelength of light, or something like that. But yeah, it's amazing how many of these units have now been defined by time, by some kind of time source, as opposed to that original meter. And if you're keen on seeing some more information about that, the original kilogram and the original meter and things like that, they're no longer, they're historical objects at this point. They're no longer used as the official calibrated measure of these things. As we said, they've been defined through other mathematical properties. But if you're curious about seeing some of these, because they are actual objects that exist, there's a few really good videos from Brady Heron. He's, if you listen to Hello Internet, he's one half of Hello Internet, the podcast, and he has a number of great YouTube channels that are sort of science related and math related. And one of his channels is called Objectivity, and he goes to different institutions and interviews the people there and shows off some of the sort of the interesting scientific objects they have. And I know that he's done a couple of videos where he's gone to see some of these original objects. The other one is Derek Mueller. He runs a YouTube channel called Veritasium, and he's done a couple of videos on some of these objects. So we'll try and dig up some of the videos for the show notes. But if you are interested in some of these historical objects that led to the original metric units, then they've both done some great videos on some of these historical objects.
And Simon Winchester, of course, goes to great lengths about this in the Perfectionist as well. So we'll be sure to link to that in the show notes too.
I think that I hadn't heard that before you started mentioning it to me, so I think I'm going to read through that, and it might be worthwhile for us to chat about a bit in a future episode, because I think there are a lot of worthwhile topics in there that relate to the things that we're discussing.
Right, definitely. He sort of closes the book out on a visit to the Seiko factory in Japan.
Oh, really?
Yeah. It was an interesting read. I enjoyed it. Everything from Rolls-Royce to jet engines to microchips to wristwatches. But as always, if you have any questions or comments, feel free to get in touch with us at hello@offhours.show. And we'll be posting all the show notes for this episode over at offhours.show/EP21.
Thanks for listening to Off Hours. You can find detailed show notes at offhours.show. If you'd like to keep up to date with the show, follow us on Twitter @offhours. John can be found on Twitter @UnderTheLoop, and Chris can be found on Twitter and Instagram @silver_hand.